Hello everyone, I am Chi Heng from the University of Colorado Boulder, and I'm happy to talk about our work on how to do efficient control synthesis for signal-temporal logic specifications using automata. As robotic systems get increasingly more advanced, there is a greater expectation for them to have more capabilities and autonomy. For example, search and rescue drones need to be able to visit regions of interest within a short time limit to successfully rescue a lost person. Surgical robots have to perform very precise motions in precise timings to complete a successful surgery, and exploration robots in self-driving cars have to plan optimally to collect rock samples or reach their destination safely. Many of these systems have complex dynamics, and so we are interested in the question of how to give guarantees on the behavior of the system when they have these time-constrained task specifications. There are many ways to express specifications, but one popular way of doing so for control systems and robotics is linear temporal logic. It allows you to express tasks in terms of the order of events. One useful aspect of LTL is that there are amazing tools that allow you to translate from the logical specification, such as the reach-avoid specification on the right, which says globally not gamma C, eventually gamma A, and eventually gamma B in any order, to a deterministic finite automaton, which is essentially a finite state machine. This gives us a graph that is easily used for hybrid system control synthesis. However, LTL does not capture real-time constraints, since the events have no time bounds associated with them. Luckily for us, there is another logic known as signal-temporal logic. This logic is defined over real-valued functions known as predicates that may be nonlinear. These predicates define regions of interest in the state space. Signal-temporal logic is defined recursively with true, the predicates, negation of phi, conjunctions of phi, and the until operator with a real-valued time interval a and b. The common operators such as disjunctions, globally, and eventually can be derived from this definition. For example, we can define the following expression: go to goal A within 6 seconds, go to goal B within 18 seconds, and always avoid obstacles, where A, B, and obstacles are defined using these nonlinear predicates. We can also consider nested formulas, where we want to go to goal A within 6 seconds and go to goal B within 12 seconds of reaching goal A. In this work, we do not consider nested formulas and focus on non-nested formulas like in example 1. For our problem, we are interested in control synthesis for a nonlinear system with STR specification defined over polynomial predicate functions. The signal-temporal logic fragment we consider does not allow for nesting of temporal operators. The problem we are trying to address is this: given a nonlinear system and a non-nested STR formula phi defined over polynomial predicates, synthesize a controller such that the resulting trajectory is guaranteed to satisfy phi. There are some related work for control synthesis for STR specifications. However, they each have an aspect that does not fully solve our problem. For example, a model predictive control technique was proposed which encodes the STL specifications into a mixed integer linear program. Another approach uses a similar technique, but finds piecewise linear paths and uses a tracking controller to follow it. These two methods can work with nonlinear systems, but only with linear predicates, and their approach is incomplete since they are solving a non-convex optimization problem. There are also recent methods using control bearer functions for nonlinear control affine systems, but they do not generally provide guarantees for task satisfaction. Finally, instead of optimization-based approaches that these previous works use, there are also sampling-based approaches which grow a tree of motions. All of these methods have one similarity, which is the assumption of linear predicates. Additionally, none of these approaches are able to solve the full problem of polynomial predicates, nonlinear systems with bounded controls, and the need to have soundness and completeness guarantees. In this work, we address the drawbacks of previous methods, and our approach is able to handle polynomial predicates as well as nonlinear dynamics with bounded controls. Our approach is also probabilistically complete and provides guarantees on task satisfaction. So, how do we achieve this? Our approach uses a sampling-based methodology, such as rapidly exploring random tree, that allows us to have a general solution to any kind of nonlinear dynamics, as long as you can sample controls and propagate the dynamics. This dynamics can be from a complex equation or even a physics simulator. However, since the robot has not just one single goal or a cost function, but a complex specification in the form of STL, the search space quickly becomes very large. To resolve this issue, our planner takes inspiration from synergistic planning approaches that improve search efficiency by iteratively using a high-level discrete search layer that biases a low-level continuous space search. And information from the low-level search informs the high-level layer at each iteration. This method is shown to be effective for complex problems. For linear temporal logic, the automaton can be used to represent the LTL specification, and the high-level search finds coarse paths in the discretized environment that satisfies the specification using this automaton to guide the low-level search. However, our problem is defined for STL, right, and not LTL. And there's not really an easy way to construct a discrete graph for this discrete search layer with STL. For those of you who know about metric interval temporal logic, or MITL, which is kind of similar to STL, you may know that there are methods to convert from an MITL specification to a timed automaton. But for the synergistic planning framework, those techniques are not really good as a discrete graph for our purposes. So, part of our contribution in this paper is how to get from our problem with STL to a hybrid system representation that allows us to use this synergistic planning framework. This brings me to the main contributions of our paper, which is the full framework depicted here. Given a time specification in the form of STL, the environment, and system dynamics, we first show how to construct a hybrid automaton and how to use a synergistic planning framework to synthesize a controller that satisfies the specification. Here I summarize our hybrid automaton construction technique. We first restructure the formula using time partitioning, such that subformulas have exactly the same time windows. This allows us to simplify construction of the automaton, since we can borrow techniques from linear temporal logic to construct a deterministic finite automaton, which we have a really good understanding and tools for. Finally, we include the environment and system dynamics to form a hybrid automaton of discrete modes corresponding to the task and continuous state corresponding to the control system itself. And the first step is to restructure formulas into subformulas with exactly the same time windows. And we can do that using the following equivalence rule for syntactic separation, where a formula is split into multiple subformulas by chopping it up at specific time points. For example, this reachable specification can be syntactically separated at time 6 to obtain a disjunction of the 3 following formulas. We can then look at which time windows are the same within a subformula, and this allows us to generate this tree-like structure where each node in the tree has the same time window. Interestingly, once we have this tree-like structure, we can now treat each node as an LTLf formula, since each temporal operator within each node has the same time window. This allows us to construct a DFA for each node separately by first ignoring the time window at the node. And once we have a DFA for each node, they are separate DFAs, so we need to combine them together. The details of this connection is explained in our paper, but if you do it carefully enough and add the time windows back at the nodes, you now have a time automaton that exactly represents the language of the STL specification. Now that we have a time partition automaton that represents the STL specification, we can add the state space and system dynamics into each mode of the automaton. We now have time windows for each mode, and transitions to the next mode is valid only if the system's time is within the time interval of the next mode. This gives us a hybrid system that fully represents our problem, with continuous dynamics in a continuous space within each mode, and transitions between modes are defined by the predicates of the signal temporal logic formula. The goal of this control synthesis problem is to reach an accepting mode in the automaton. So, is this enough to use with our synergistic planning framework? Now that we have the hybrid automaton, how do we actually use this in the synergistic planning framework for efficient guidance with the high-level discrete search? We cannot directly use it because the dynamics are continuous after all. To do this, we discretize the environment geometrically, such that we get a discrete graph that represents the environment in each mode. This space discretization is solely geometric and does not require knowledge of the system's dynamics. There are many tools from computational geometry that allows us to work with polynomial predicates. Now, we can finally use our multi-layered synergistic planning framework with the constructed automaton. To do this, we start with the high-level discrete search layer, and we use a graph search algorithm such as Dijkstra or A* on this discretized automaton to find a discrete path that satisfies the formula. For example, one solution could be the modes in red. This may look something like this in the discretized environment. At the low level, a tree-based motion planner is used. In this approach, any tree-based motion planning method, such as rapidly exploring random trees or RRT or expansive spaces tree or EST, can be used. The low-level search grows a tree of motions by sampling controls from nodes of the tree and attempts to follow the sequence of discretized partitions in the environment. This way, the low-level search has a geometric guide that tells it which parts of the state space are worth exploring. However, since the discrete path given by the high-level search is based on the geometry of the environment, it may not be possible or very difficult to follow because of the system dynamics. Therefore, information such as how difficult it is to grow the tree to follow this discrete sequence is fed back into the high-level planner and the next iteration starts. With information from the low-level layer, the weights of the edges of the graph are updated and the discrete search finds a new geometric solution. The low-level tree search now has a new sequence of discrete states to attempt to follow. Note that we do not abandon nodes that have already been grown in the tree because they may be useful in future iterations. Another iteration occurs, the graph is again updated, and a new geometric guide is found. This synergistic process repeats until the motion tree finds a motion that reaches the accepting state of the hybrid automaton, which means it successfully satisfies the specification. This was a simple example with just reaching a single goal and avoiding obstacles, but our proposed method is effective with more complex specification due to this synergistic planning framework. So what guarantees do we have? Firstly, we show that our automaton has language equivalence, where a time path is accepted by an automaton if and only if it satisfies the STL formula. This tells us that using this automaton is useful for planning, since finding a path to an accepting state guarantees us that the STL formula is satisfied. Quite similarly, we also have correctness or soundness, where a trajectory returned as a solution of our framework is guaranteed to satisfy the STL formula. Finally, we have probabilistic completeness. Since our approach is using a sampling-based method, our algorithm finds a satisfying solution with probability 1 as time approaches infinity. So, how does our method perform? We first looked at specifications defined over linear predicates, since most of the previous works could only handle linear predicates. We conducted benchmarks for two specifications and systems. The first specification was for a double integrator system, which has a formula that says, between 2 and 10 seconds, go to the green region, and between 0 and 10 seconds, every time the x component of your state is within 2 and 3, y has to be above 0.5 or below minus 0.5, which corresponds to the blue region. But for the first 2 seconds, you want the y component of your state to stay within minus 0.5 and 0.5, which kind of corresponds to the black region. We compared our approach to a sampling-based motion planning approach that does not utilize automaton. Given a 30 seconds time limit, we report the success rate and the time taken to find solutions for successful runs. As seen from our table, our automaton-based approach is able to find solutions very quickly, slightly faster than the comparison approach. We then looked at a more complex system, a second-order unicycle with a simple timed reach-avoid specification, which is reaching the green region within 10 seconds and avoiding the black region for 6 seconds. We can see from the table of results that our automaton-based approach is able to find solutions very quickly with high success rate, while the non-automaton-based method struggles with finding solutions when the system becomes slightly more complex. Next, we wanted to study how time partitioning affects the search for a solution. Recall that we need sub-formulas to have the same time windows in order to use LTLf techniques to construct our automaton. For example, in this STL formula, which is already partitioned from 0 to Ti and Ti to Tf, we can directly construct an automaton that looks like this. However, we can actually do finer discretization of time than necessary, and this leads to a larger automaton that has a finer granularity in the time dimension. When it comes to guiding the motion tree, our hypothesis is that high-level plans could become more detailed and be able to guide the low-level search better. So, we ran experiments to see the impact of time partitioning, and this is what we found. As seen from the figure on the left, we see that as we increase the number of additional time partitions, we observe a higher success rate of finding solutions initially, since the high-level discrete search of the synergistic planner is able to give discrete paths with better granularity in the time dimension. And as you start getting too many partitions, the hybrid automaton gets so large that the synergistic planning framework cannot find solutions well. So, there is a trade-off in terms of the number of time partitions you want to additionally include. Similarly, on the right we see that among the successful runs, as you increase the number of partitions, the time taken gets larger and larger. So, there is a sweet spot where you have a high success rate and a decent amount of time taken to find solutions that is problem dependent. Finally, to showcase the capability of our planner, we looked at a car-like system with nonlinear dynamics and an STL specification where the regions of the state space are defined with polynomial predicates. In this example, our specification is to go to the blue region within 10 seconds, go to the green region within 20 seconds, and always avoid the red region. Our planner finds a solution in less than 5 seconds, and what it does is it goes to the blue region, makes a U-turn, and goes to the green region, satisfying the specification. In conclusion, we propose a hybrid automaton construction technique for signal temporal logic for nonlinear dynamics and polynomial predicates. We also proposed a planning framework that is correct by construction and probabilistically complete. Results show that time partitioning and automaton-based approaches can improve search efficiency for control synthesis of STL specification. For future work, we are looking at how we can do automaton construction for nested STL formulas and also incorporate motion and measurement uncertainty. Thank you very much for listening, and please contact me if you have any questions about our work.